Hello, everyone. Thanks for joining me again today. I hope you had a lovely weekend, and I got myself some coffee, and I think I'm ready for the next challenge. And just a refresher, what that next challenge is. It is again the positioning of blocks and clashes between blocks and connections, and also connections and connections. So we have 3 problems to resolve. I don't have good ideas how to do that yet. I did spend some time over the weekend. You can probably tell by these connections looking a little bit different. I did spend a little bit of time over the weekend thinking how we could resolve at least some of those problems, but I don't have any good ideas yet. I have one idea that I want to explore, but I'm not sure if it's good. So just a refresher. I discovered a problem with the connections. If they are going from like a very narrow set of blocks to another narrow set of blocks, and they need to go through a wider set of blocks like here, they start clashing with that set of blocks. Because the width is calculated for this narrower set of blocks. That's one problem. 2, the connections still clash with each other on the y coordinate, but that I wouldn't consider to be my immediate focus, but it's still a big problem. And the third problem, which is probably going to be my first focus, is the fact that the amount of space that we need to leave between the right-hand side branch of a fork, in our case, question 1, you can probably not see it, but that's question 1, and the left-hand side branch of a fork is dependent not only by connections leading to the fork and its children, but also by the connections that need to bypass all the blocks and connections that happen somewhere in between these connections. So this major block. So we have a bit of a chicken and egg situation. How to position blocks if we don't know the position of the connections, and how do we position connections if we don't know blocks? So the answer I have today is just multiple sweeps. So right now the idea I want to explore is, let's not position the right-hand side of a fork based on the width of the left-hand side of the fork as we do it today. It sounds reasonable, but it just wouldn't work with these connections. Instead, determine the position of the right-hand side branch of a fork based on not only the width of the left-hand side, but everything that happens after it. So this fork, these 2 actions, or this one action and this huge fork, and also this fork and these 2 actions. So I'm not sure how visually pleasing that would look like, but it's an idea to place a right-hand side block over here and not maybe a little bit closer. But if we do so, we're carving out space for the possible connections that might be connecting, like action Z5 or whatever it is, to one of the earlier blocks. If there are connections, it probably should look fine, or connections like that, it probably should look fine. But if there are no connections like that, the spacing between the left-hand side branch of a fork and the right-hand side branch of a fork could be questionable, but I suppose we'll see. So for today, I just want to have a short session during which I implement the width of a collection of skewer blocks. Oh, sorry, I keep using the term skewer blocks. We don't have skewer blocks anymore. It's just blocks. Today we can precisely determine the width of a block with all connections leading to it. But we're assuming that those connections are leading from like a more narrow set of blocks, not through the wider collection. So not to make the introduction too long, we basically need a function that calculates the width not only of a fork, but of a collection of skewer blocks that include the fork and go all the way down to the end of the skewer. I'm not sure how I'm going to use it yet, and I prepared a little bit of an algorithm for me to follow, but I just don't think that's a good idea. So my idea was to the origin of OP. I don't even know what it is. Origin point? Origin parent? Oh, origin parent. Navigate upstream recursively to find origin's topmost parent. Navigate upstream recursively to find destination's topmost parent. And this is to find the skewer block, the block from which we should start and end our calculation of widths. And then sublist sublist the main list of blocks, start with the origin parent and destination parent. So say we take a sublist here from question A to, in our case, question Z. And we basically check all those widths, determine which one is the longest, and we continue. So, but since then, I discovered that probably this is not the best idea still, because how do you navigate recursively upwards from a block to its parent? We would have to change so many types. What we do know, though, is the level at which a block resides. So if we already have a function that determines the width of a collection of skewer blocks, and it's here. So we could just change the signature from double to a list of, list of doubles, or even a map of doubles where the ID is the level at which a block resides, and the value is that level's width, which we can calculate. So I'm pretty sure this is not going to be our long-term idea for determining widths and positions of blocks and connections, but at least it will be a start. So I'm hoping for another short session today, and let's see how it goes. That was a very long introduction. So what I have in mind is, say we want to use a map. And it's a weird looking map, but we can use it nevertheless. So the function would look something like this. And let's try to call it. Let's use the trusty function peek. And to save time, we don't even need this. Oh, the map returns a list, so we'll have to find a function that projects a list to a map. Let's do it. Yes, to convert we'll need a pair. But it's okay. We can still use a fold here. Let's call it W for width. And we'll have to use a tuple. The first element is going to be a counter, and the second element is our map. Let's call it index. And Oh, it also takes this list. So we only have 2 levels, do we? We actually might. Let's just refresh our memory. This is 1. And the other one is probably question 3, if I'm not mistaken. Let's check the code. That's 1. And it's very wide, 23.5. And the other one is question 3. Which is just regular 6. So that function that function will not work. Because we're only tracking we're mapping levels incorrectly to the blocks. Well, this is indeed a pickle. I warmed up my fingers on this function, but that is not going to provide much value. But I still do believe, and this is probably where we're going to wrap the session up for today, but I still do believe that we could benefit from having a function like this that returns a double, which is the max width between 2 blocks. Block 1, block 2, and it returns a max width. Or block ID, but not all blocks have an ID. And that max width could be used in this function, formulate gamma connection, where we have direct gamma connection origin, direct gamma connection destination, and width. And that width could be supplemented with the max width of all the blocks between those two blocks. See, if we run a quick test, and we do, say, +3, or +3.1, because it's easier to find. Let's go back to previous values. Using 0.5 was not the best idea, because it clashes with other names. Okay, so if we just artificially add 3.1 to our current diagram, if we actually render it, yeah, it should be fine. Oh, I mean, connections are fine, but these will still have to move. An idea we might explore during some of the later sessions or upcoming sessions is when we render and we update origins with all these IDs, we technically have origins of all blocks here, or access to all blocks here. So after the rendering function finishes, technically we should have all of our origins which is again not exactly what we want, because origin is a map of ID and a point, if I'm not mistaken. ID and a point, yes, that's an origin. But if we have a 2D list where the rows are diagram rows, and or even a list of tuples, where the first element of each tuple is the depth of the list, or the row index, or whatever I want to call it, and the second element is the width of that row, we know the origin, we know the destination, so we can technically determine what's the max width between two rows. But here, here, sorry. But that function cannot be properly called on its own. But instead, it can only be called after the rendering is done. Yeah, I think I might explore that during upcoming sessions. So these widths obviously don't work because in our current collection we only have 2 blocks. Everything else is just nested within those 2 blocks. But if we really charted it level by level, we would expect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 levels. Let's leave a comment for the next session. Okay. I'm not sure how we're going to do it yet, but I think it will have to do. It will have to have something to do with rendering functions. All right, I think that's good enough for today. I'll keep thinking about this. Maybe I can think of something else. So in the meantime, thank you all very much for your attention, and I wish you a fantastic week ahead, and take care of yourselves.